Welcome everybody. We are the small scale solar team. My name is Alan and my colleagues are Brian and Ivan. So we all know that fossil fuels are very inefficient and dangerous. As you get to see that our main sources for fossil fuels are going towards transportation and industrial factories. It's caused a lot of greenhouse gas emissions, and it's pretty uncomfortable for us to live in this situation. Fossil fuels cause pollution in our water, land, and air, and also so let me give you an example of an ATN that's already out there, AirTrain. AirTrain is powered by hydroelectricity alone. This you can see it from the data sheet right here. You don't necessarily need to read the whole data sheet, but this is a data sheet they collected from 2009, 10, and 11, and it gives us the greenhouse gas emission mitigation or offset. More specifically, you can see that 2009, 10, and 11, they saved a lot of resources from this, from switching towards AirTrain instead of relying on shuttle buses and taxis. You could also see that they start decreasing in greenhouse gases emissions throughout 2009, 10, and 11 on the right side of the screen. So this is going to be our first powered ATN, and we're going to rely on solar panels, which are very low to no cost maintenance, very it's free energy, and but we are in the United States. We usually rely on fossil fuels, and it's 85% Americans we rely on fossil fuels. So and you can see that coal and nuclear is one of the most, I guess, our fuel sources, and so this is why we need solar panels.
So I'm going to talk about the state-of-the-art literature. There are 3 commercially available solar panels as of today. The first one being monocrystalline silicon. It has an efficiency of around 15 to 20%. It is the highest purity silicon solar panel of the 3 kinds. This is because of how it's processed. Much of the wafers that are on the solar panels are cut from a single silicon crystal, as opposed to the polycrystalline silicon. It has an efficiency of around 13 to 16%, and that's due to the way it's manufactured. Instead of being cut from a single silicon crystals, it's actually cut from different crystals. This allows the crystal lattice of the silicon to be discontinuous and kind of have inefficiencies there. The next thing is thin film solar cell. It's the one that we're looking towards today. It's around 7 to 13%, but companies like Miasol are bumping up their efficiencies to around 16%. The major advantages of using this is it can be formed in any shape or form, increasing the efficiency, but the downside is that it lasts a little bit, lasts less longer than the other 2. And the last one, it's not in commercially available today, but it's a lab grade called absolute black silicon wafers. It has a efficiency of around 99.7%, and that's due to the lab environment that it's in. A lot of the debris and the dust are ridded from the environment, but that's not the case for the solar panels that we're using. So when it comes to solar panels, orientation is key. The solar panels need to be at the optimal angle relative to the sun, and also the shape of the solar panel does take into account, such as curved or convex, concave. They do boost up the efficiencies. So one of the examples of orientation is last year's solar tracker for the small scale. They had a single tracker for their track, but we wanted to build a dual tracking system for this year's scaled model. It can rotate 2 directions as opposed to just one. And here's Ivan for the rest of the functional specs.
All right. To continue on about the functional specs, we're going to be using an external solarized power source to fully solarize the system. It's going to be a system very similar to what a solar farm is. The reason we chose this is because of certain challenges we have to overcome. We believe this is the only way that we can achieve a fully solarized system. The benefits of having this power source is that we are not limited to the track location or the track size. The solarized farm will consist of three thin film solar panels that MiaSol provided to us. These will be full-size panels, however. The solar panels types that we'll be using are thin film panels. The thin film, as Brian stated, are the least efficient. However, they are the least expensive and can mold to any shape. We'll be using these for both the tracking panels and the solar farm. The efficiency is about 7 to 13%. The small scale panels offer about 1 amp per 10-inch panel, and MiaSol offer about 11 amps per panel. Certain challenges that we had to overcome. One is that thin film panels do have several setbacks. One is that they degrade the quickest. 2 is that they're the least efficient. And I think 3 is that our scale panels only offer about 1 amp per 10 inch, which I'll explain more on this slide. I believe our biggest challenge will be about the bogey requirement. Each bogey requires about 3 to 4 amps right now. As I stated earlier, the 10-inch panels only supply about 1 amp. This is the reason why we chose to go with the solarized power system. We're going to need, talking to the bogey team, we're going to need about 35 amps at max because they want to implement about 10 bogeys. So that means we're going to need a lot of power just for not that much panels. Some of the goals for the solarized scale team. Our first goal and number 1 goal is to create a fully operational solarized system. This has been the goal since the start, and we would like to stick to that, and we believe it's possible. We are planning to create a passive solarized station and creating a dual axis solarized station, as Brian stated earlier. Both these will be very beneficial. Both of them will be on the track and be scaled to size. We'll be needing a budget about $750 to $1,000. The budget will include solar panels, inverters for both scaled and full-size model, and batteries. Here's a quick look at our Gantt chart. We have assigned team roles as well as individual roles. And here's a team member responsibility. I myself and the team lead, I will be communicating with other teams, managing budget, and checking progress. Brian will be doing the research, documenting data, and ordering parts. Alan will be the design lead. He will also be 3D rendering and fabricating. Any questions?
More observations. Be really careful with your units. You guys are messy with your units throughout the entire presentation. Amps is not a measure of power. It's a measure of current. So if you don't provide the entire amps at what voltage, you're not providing your story. Compare a couple of different solar cell technologies. You talk about efficiency. And at the very end, you mentioned this incredible jump. And you go to like a 99.7% efficiency or something, but you're confusing light absorption versus efficiency of power generation. So you're mixing up a story there, where you're presenting this pie-in-the-sky concept that can't provide the numbers that you're presenting. And earlier on, you talked about the resources that are being saved by the electrical system over at SFO. Mm-hmm. What are those resources?
They have a climate control plan, and they usually have, it's not AirTrain itself. They try to eliminate near zero, they're trying to reach the near zero emission, they have shuttle buses and taxis and other forms of transportation, and they're trying to make a cleaner climate.
Are we talking about like pounds of CO2? Are we talking about large carbon particles? What are we talking about?
Greenhouse gases emissions per ton per year, or ton per year.
On that chart, present what you're talking about. There's no units there, so those numbers become meaningless.
understand that you guys want to propose a tracking system?
Just for the stations.
And why is that?
They wanted to, for the intermediate scale, they wanted to do a dual axis tracking system for one of them, so we wanted to do one for a station.
Why? Why dual axis tracking? I mean, I know the answer, but what does tracking do for you, and why are you going that way?
It maximizes the power efficiency by changing the angle.
By how much? You got to have a motor, you got to have all this other stuff to do that. What are you, in a sense, getting for that ability that you want to put in there?
Sorry?
Well, why not just make it all passive?
Well, passive, you can't move the solar panel to the right angle and have all of the, I guess, solar energy to maximize the solar energy.
Yeah, but it's very easy to do and it's cheaper and it doesn't break. So, I mean, what's the justification for wanting to do the tracking system?
I think we
It has
also
to be, you got to have some reasons to go that way.
we saw that or we heard that the intermediate scale was trying to implement a dual axis,
Yeah.
which is why we chose to go that way as well.
So your reason is some other guys were trying it, so we're going to try it too. Is that?
Well, we just thought that we were supposed to make it a scaled down version.
But suppose they made the decision and it wasn't a good decision. And so, right? That's one of the things you want to think through is, does that make sense? I don't think it does. When you look at most of the solar that's out on rooftops, that's out on parking lots. The only system I know that I've seen that's fairly large is Deanza's parking lot. It tracks. That's interesting. But what's the trade-off for that? It's mechanically more complex. It probably costs a significant amount more than if it were passive. Do we need that? I don't know. Those are some questions. So, you don't want to commit the project to something that may not be the best. And so, I'd like to see some reasons for why you want to do tracking.
And add a small add-on to that. Are you guys familiar with the term ROI, return on investment? This is something that comes up in every engineering discussion I've ever been a part of, really. So you make the assertion that this tracking system is more efficient. It's going to be some percentage more efficient, which means it's going to generate some amount of energy. Which means sometime in the future, you will have saved enough energy, you'll have generated enough energy to pay for those motors, and pay for the complexity, and pay for the upkeep. Will the motors last long enough to pay for themselves? If not, maybe it just makes more sense to go out and replace panels or put more panels out there. So that's it's a very engineering thing to think about. By adding this complexity, can I, at the end of the day, make my money back with those efficiency gains?
Did you guys look at the Uppsala study that the students from Uppsala did on solar? Okay. So, Ron, do you have any input on, were they looking at tracking systems in Uppsala? No tracking system? Okay. So, I'd like you guys to look at that. It's on the NIST library site. I think you have access to that. But look at what they've done. And I think that what can be done at the full scale, intermediate scale, and your scale, I think that a well-designed passive system can do what we need to do. I'm not sure of that, but at least the students from Uppsala, they did a full scale, like city kind of viewpoint at a very high latitude, right? Sweden is like way up there. It's not like here. Here, you could probably get by with less width of panels than they were looking at. But their studies seem to say that it could be done all passively. So take a look at that. Questions? Okay, guys, got some more work to do on this, okay? Thank you.